Okay, Algebra 2. We're solving polynomial equations, which means we're trying to find the number of zeros. We found that we can factor. We found that we could graph them. We found that we could use a quadratic formula or completing the square if they were quadratics. Those are all methods that we can do it. But sometimes we just need to know how many roots or zeros or solutions, whatever you want to refer to them as, that we need. And there was a mathematician by the name of Alg2 Descartes who kind of came up with this idea that we could find out how many we need to find. His name is Descartes, and let's see what his rules are. Descartes' rules of signs. The number of positive real roots is equal to the number of sign changes between consecutive terms of p of x, or less than that by an even number. Why an even number? The reason is imaginary numbers. Imaginary numbers always have to come in a pair. There always has to be the positive I and the negative I so they all cancel out. Back when we did those conjugates. So, how do we use this? We always start with a polynomial in standard form. So here I have one down below here. I've got p of x equals 6x to the fourth minus 13x cubed plus 13x squared minus 39 minus 15. And I want to look to see how many positive real roots they are using Descartes' rules of sign. The first thing I would ask, though, is how many number of roots are there all together? And if you think back when we did the fundamental theorem of algebra, it said you've got to look at the highest degree exponent. Here we have a 4. So the number of roots we're going to have for this particular case will always be 4 because we have 4 roots there. Now, they might not all be real. Now, how many positive real roots? According to this, I got to count sign changes. Well, notice this is a positive 6x to the fourth, and right here I have a negative. So that's one sign change. And now my next term is a positive. So that's 2 sign changes. And now I notice that my next one here is negative. That's 3 sign changes. And then the last term is negative. So I had 3 sign changes. So I would have a possibility of 3 positive real roots. But then notice this, or less than that number or less than that by an even number. So 3, if I go down by an even number, go down by 2, that would say 1. So I could have 3 or 1 positive real roots for this particular problem. The question is, which would I have? Don't know. Not until I started checking them. Now, Descartes also said that you could figure out how many negative real roots there are as well. He says the number of negative real roots is equal to the number of sign changes between consecutive terms of p of negative x, and less than that by an even number. So I need to find p of negative x. So in my example problem, I have a p of negative x equals, but I don't have anything there. How do I figure out what p of negative x is? Well, what I do is I rewrite the polynomial by substituting negative x in for every x. So that would mean I would have a 6 negative x to the 4th power minus 13 negative x to the 3rd power plus 13 times a negative x squared minus 39 times a negative x minus 15. Well, now I'm going to have to clean that up. A negative x to the 4th power would be 4 negatives. 4 negatives is even, so that would be positive. So that would stay the same as 6x to the 4th. Now, negative x to the 3rd power will be 3 negatives, so that would be negative. But there was a minus in front of that 13, so that means actually I had 4 negatives in that problem, which would say I have a positive now. So it's a positive 13x to the 3rd. And now negative x squared would be positive. And there was a positive in front of the 13, so it would stay positive. Then I got the minus 39 times the negative x, 2 negatives. So that would become a positive. And then I have the minus 15. So I have my p of negative x is 6x to the 4th plus 13x cubed plus 13x squared plus 39x minus 15. So now I'm looking for the number of negative real roots. Well, according to this, after I have p of negative x, I count the number of sign changes. So we're going to go through that again. I have a positive 6x to the fourth, and a positive, and a positive, and a positive, all the way down to 39x. And then I have a negative. So right there, I have one negative real root. So no matter what, I have one negative, and I guaranteed one positive for 3 positives. So that covers positive negative real roots. But according to the fundamental theorem of algebra, the number of roots could be complex. So it means I could have imaginary roots. So here's the way this works. I can calculate the number of imaginaries based off of what I've already known. I know I have the option of 3 positive reals and 1 negative real root, and together they would account for all 4 of my roots. So if I started with my left-hand column here, my 4, and I subtract 3, and I subtract the 1, I get 0. So it says I could have 0 imaginary roots. Well, now my next option is I got 4, and I could take away the 1 positive and the 1 negative, which would say I have 2 imaginaries. So I either have 3 positives, 1 negative real root, and no imaginaries, or I got 1 positive real root, 1 negative real root, and 2 imaginaries for this example. Let's try another one real quick here. So my example is 9x to the 5th minus 4x to the 4th minus 2x cubed minus x squared plus 5x minus 15. So again, I'm going to look. First thing I notice is the highest degree is a 5. So since my highest degree is a 5, I know all of my roots have to be at most 5. Well, now let's look at sign changes. I got a positive at 9x to the 5th, and I got a negative 4x to the 4th. So that's one sign change. But then it's negative, then it's negative. I don't get another sign change until I get down here to the negative x squared plus 5x. So there's my second one, and then I go from positive 5x to negative 15. That's the third one. So I have 3 positive real roots, or 1 positive real root. So I'm going to put the 3 and the 1 down there. Okay, so now I got to find p of negative x. Now here's a quick little thing. I know I got to put negative x in for every one of these and then simplify it. Here's the thing I notice. Wherever there's an x with an even exponent, the negative x is going to come out as a positive x. And whenever it's in an odd exponent, it's going to come out as negative. So this becomes a negative 9x to the 5th, but the 4x to the 4th will not change because a negative x to the 4th power is going to be positive. I would still have that one negative. Now my 2x cubed is going to change because the negative x to the 3rd power with another negative out in front, and then the next one does not change, and the 5x would change, and I end up with that. So my p of negative x is a negative 9x to the 5th minus 4x to the 4th plus 2x cubed minus x squared minus 5x minus 15. If you want, plug the negative x in and work it all the way out. You'll get that. So now, again, the first thing I want to do is I want to look for sign changes. Negative, negative, oh, here's a negative positive, there's 1, and a positive negative, there's 2, and a negative positive, there's 3. Oh, sorry, that was negative, negative at the end. So, mess that up. Minus 5x minus 15. I only have 2 positive real or negative real roots. So that 2 could be with the 3, or the 2 could be with my 1 positive real roots. Well, I also can take this down by an even number. Well, 2 minus 2 would be 0. So it's saying I should also have a possibility of 0 roots with my 3 positive real roots and my 1 negative real roots. So now I have an option of 3 or 1 positive real roots. I've got an option of 2 or 0 negative real roots. So imaginaries, I'm going to go through that list again. I'm going to take 5, and I'm going to subtract 3 and minus 2, and that gives me 0. Or it could be 5 minus 1 minus 2, which would get me 2. Or it could be 5 minus 3 minus 0, which would say still 2. Or it could be 5 minus 1 minus 0, which would be 4. So my options here for positive roots are 3 or 1. For negative roots, it's 2 or 0. And for my imaginary ones, I can have 0, 2, or 4. roots. And that's kind of what my table helps me find out for that. Okay, so now the other thing I have going with this assignment is, can you go the other way? Here are the roots. Here are my zeros. 2, -3, and 4 minus 5i are my roots. Now, if they're whole number, if they're real numbers, like we have here to begin with, the 2 and the -3, those are all we would have to do. Anytime we get an imaginary number like this last one, we always have to have its conjugate with it. So if 4 minus 5i is a root, we automatically know that 4 plus 5i has to be a root. So anytime it's an imaginary one, we always have to have its conjugate with it. So now what do we do with this? I let each of these equal x. So x would equal 2, x would equal -3, x would equal 4 minus 5i, and x would equal 4 plus 5i. Now, I want to set each of these equal to 0. So that means I got to move the 2 to the other side, so it would be x minus 2 equals 0, or x plus 3 equals 0, or x minus 4 plus 5i equals 0, or x minus 4 minus 5i equals 0. So I'll let each of those equal 0. Now, I'm going to eliminate the equals 0 part and multiply the rest of them. So the x minus 2 times the x plus 3 times the x minus 4 plus 5i, and the x minus 4 minus 5i. I'm going to take all those and multiply them out. Now, when I multiply these out, I'm going to multiply the imaginary ones together, and I'm going to multiply the non-imaginary ones together through FOIL or whatever method that we need. So when I do that, I'm going to get an x squared plus an x minus a 6 for my real part. For my imaginary part, I'm going to get an x squared minus a 4x minus a 5ix minus a 4x minus a 16 minus a 20ix, and now the 5i, so I get a negative, or I get a positive 5ix. Oh, that negative 20x, that's wrong. That's not an x. Back up, hold the phone. So I'm going to take the negative 4. I got a negative 4 times x. It's a negative 4x. Negative 4 times negative 4 would be the positive 16. And then the negative 4 times the negative 5i would be a plus 20i. There we go. And now I'm going to take the 5i through all of it. So I got a positive 5ix and a minus 20i and a minus 25i squared. So now I got to clean this all up. I still have my x squared plus x minus 6. The real parts are the easy ones. Here I have an x squared minus an 8x. The ix's cancel off. I've got a plus 16. My 20i's cancel off. And I got a minus 25i squared. Now, as we know, I squared is a negative 1. So this is really a plus 25. So I really have an x squared minus 8x plus 16 plus 25. Well, if I clean that, that's an x squared minus 8x plus 41. And then I have the x squared plus x minus 6. Now all I got to do is multiply these two trinomials. So that's an x to the 4th minus an 8x cubed plus a 41x squared plus an x cubed minus an 8x squared plus a 41x minus a 6x squared plus a 48x minus a 246. So now if I clean all that up, I got an x to the 4th minus 7x cubed minus 14 plus 27x squared minus an 89x minus a 246. So P of x would equal this. And all I did was start with those roots and work it out. So whenever you get the roots to begin with, you're going to set them equal to, let x equal those. then get them all onto one side by doing the opposite so that they're all equal to 0. Then you're going to take each of those individually, put them in their parentheses, and multiply. Always multiply the imaginaries first, because that'll get rid of that I, and then you can multiply through. When we're doing Descartes' rules of signs, and we're trying to figure out how many roots we have, start with fundamental theorem of algebra, and that's that highest exponent, and then count the number of sign changes. Okay, that's the theorem.